All right, so now I want to attack the problem of determining the definiteness of any quadratic form. And one thing to keep in mind is that since quadratic forms are represented by symmetric matrices or real symmetric matrices, we should be able to take advantage of the spectral theorem. The spectral theorem is a very special theorem that applies to Hermitian matrices and therefore also to real symmetric matrices. What I want to do here is I want to show you the method of what's called completing the square for any quadratic form. So let's say we have a spectral factorization, S equals U times D times U transpose. Remember, what this means is that U is unitary, meaning that its transpose in this case, because everything is real here, is equal to its inverse. And D is real diagonal. Well, if we look at the quadratic form, this is the inner product of x with s times x, and we can substitute in our formula for s. So this is really x inner product with u times d times u transpose times x. And now we can once again take advantage of the adjoint formula. I can move this u on the right to the left, but when I do so, I have to transpose. So now I'm looking at the inner product of u transpose with x with d times u transpose times x. What we're going to do now is we're going to introduce a change of variables. I'm going to define y equal to, so this is a new vector called y, this is equal to u transpose times x. So now I'm looking at the inner product of y with d times y. And what's cool about this change of variables is what this is saying is that the original quadratic form could be very complicated, but after changing from x's to y's, the quadratic form is not so complicated. Because d is diagonal, all I'm doing is I'm taking the first eigenvalue of s, multiplying by the first coordinate of y squared, plus the second eigenvalue, lambda 2, multiplying by y2 squared, and I keep going until I get to the last eigenvalue, lambda n, where I multiply by yn squared. So this takes our generically ugly quadratic form, and as long as we can find a spectral factorization, we can write that quadratic form as a linear combination of square terms. So this process is called completing the square. So let's see this in action. So remember, to complete the square, you have to have a spectral factorization. So here I have a spectral factorization of a real symmetric matrix S. This one's a 3 by 3. So what does the spectral factorization get us? Well, to complete the square, remember I had to change from x's to y's. And when I change from x's to y's, in this case, since the eigenvalues are 6, 3, and 0, I know that my quadratic form is 6 times the first y squared plus 3 times the second y squared plus 0 times the third y squared. Great. Well, what are the y's here? Remember that the vector y is u transpose times x. So what I'm doing is I'm taking inner products of the rows of u transpose with the variables x1, x2, and x3. So y1 here will be 1 over root 2 x1 minus 1 over root 2 x2. Again, that's the inner product of the first row of u transpose with x1, x2, x3. y2 here will be the inner product of the second row of u transpose with x1, x2, x3. So this is 1 over root 3 x1 plus 1 over root 3 x2 plus 1 over root 3 x3. And then y3 here will be the inner product of the third row of u transpose with x1, x2, x3. So I know what the y's are in terms of the x's. So I can make those substitutions here, and I get a formula for my quadratic form. If I clean up the arithmetic a little bit, I get 6 multiplied by the quantity 1 over root 2 times x1 minus x2, all quantity squared, plus 3 times 1 over root 3 times x1 plus x2 plus x3, all quantity squared. And actually, I can clean this one up a little bit more. If I square 1 over root 2 and multiply by 6, I get 3. And if I square 1 over root 3 and multiply by 3, I get 1. So this quadratic form ends up being able to be written as 3 times the quantity x1 minus x2 squared plus the quantity x1 plus x2 plus x3 squared. And we get this nice factorization, or this nice form of the quadratic form, because we were able to complete the square given the spectral factorization. One thing I want to point out here in this example is this quadratic form is 3 times a square plus another square. We're working with real numbers here, so this will never be negative. So this is an example of a positive semi-definite quadratic form.